Good day, dear students. I'll be dealing with magnetism today. I'd like us we discuss this because it's a topic that is very common to us. Everyone is familiar with magnets, right? Now we will be speaking about the physics behind a magnet, right? Um, First of all, we know that there is what we call a magnet, right? And if you take a magnet um, and you push it or you put it closer to any metallic substance, it will most likely attract, right? I'm saying metallic on purpose because most metals are magnetic or have the magnetic properties, right? So that is what we will be dealing with. The reason why what we'll be dealing with is the reason for the magnets to eventually or for the objects, right, to eventually come to eventually be attracted to one another, the physics behind that, right? Right, let's get to it. Let's first understand the term magnetism. When we're speaking of magnetism, we are speaking of an interaction that allows certain kinds of objects which are called magnetic objects to exert forces on each other without physically touching, right? This is what an interaction, um, okay, when we say an interaction, take this for example, these two blocks here to be objects. Let's say this is our objects. They're saying is when they interact. When we say something interacts, it means that there is an input and an output, right? Now, the magnetism is the interaction that allows certain kinds of object with magnetic what? Certain objects which are called the magnetic objects, right? Certain objects, not all objects. Magnetic objects, these are objects that have the magnetic properties, right? And we'll deal with the magnetic properties as we continue. Now, these objects exert forces on each other without physically touching, right? Although they are closer together, they do not touch each other. That is magnetism, right? These two objects, they have the magnetic properties. Having the magnetic properties, they do what? They exert forces on each other, but they do not touch, right? They have what we call the non-contact force, right? Now, when we speak of a non-contact force, we have different types of forces, right? Number one, we know that we have the contact force, right? Number two, we know that we have the non-contact force, right? The non-contact force, right? These are the mainly, we know that when we're speaking of contact forces, we speak of the applied force, right? We know that we are speaking of what we call the friction, right? We know that we are speaking of the kinetic friction, or let's just include that in friction. Friction will include the static friction, right? The static friction, Fs max, and the kinetic friction, which is the Fk max, like that. Now, this is the force applied. This is the frictional force, right? What else? We can speak of the tension force, right? Yeah, and so on. Right. Now, when we speak of non-contact forces, the first force that comes to mind is going to be the what? The normal force. the force of gravity, right? And so on, right? Now, all of these forces, they form a certain identity, right? Now, but we are not going to be speaking about them, but I want us to understand this concept is that these objects, they exert forces on each other without touching, which means they contain this non-contact force, right? With non-contact force here, we can still add the magnetic force, right? Because when we speak of the magnetic force, we mean those objects that have the magnetic properties, they come closer together and they exert forces on each other that will either cause the objects to attract or repel, right? Remember, a bulb magnet experiences a force long before it touches, or long before let's say long before it touches an object. Meaning, if it's going to attract an object, you will feel it if you're using your hands, you will feel it when it gets a bit rough, or when the movement is no longer as smooth as it used to. Now, when it's going to, similarly, when it's going to repel, it's going to do the same. You experience, there is a force that is experienced either to or away from, right? That is what we that is how we define a magnetism. Now, inside magnetism, we have what we call the magnetic field. The magnetic field. Now, what is a magnetic field? Magnetic field, this is a region in space where the magnet or an object made of magnetic material will experience a non-contact force, like I said in the above statement, right? The magnetic force. This is the region in space whereby an object will experience a non-contact force, will experience a what? A non-contact force, right? Contact force. You'll excuse my handwriting on this, right? Non-contact force called the magnetic force. The magnetic force, right? This is practically what it's a phenomenon, if I may add. It's not necessarily a phenomenon, but a region in space whereby an object will experience a non-contact force known as the magnetic force, right? That is what we call a magnet. This is a region in space where the region in space. When we say a region, we mean around the object, right? This is the object, right? And this is around. This is the region in space around the object, right? Now, we have different types of magnets, but all of them, or rather, let me not say we have the ferromagnetic, we have the ferromagnets. Let me say the ferromagnets, right? The ferromagnets. Number two, we have the permanent magnets, right? Sorry, a permanent. Yeah. Let me rewrite that. A permanent. Let me rewrite all of them. All right. We have the ferromagnets. Ferromagnets, right? We have the permanent magnets. Right? Now, the ferromagnet, they have the ferromagnetic properties, right? What are the ferromagnetic properties? Um, when we say something is ferromagnetic, we only we mean, okay. Before, when we define a magnet, we define it by its domain, right? Now, the ferromagnet, its domains, uh, in its domains, we can say in each domain, the electron magnetic fields, right, are pointing in the same direction, causing a net force or a net magnetic field, big wide arrows to be in each domain. Now, they go in the same direction, they all point in the same direction. Okay, let me try to explain the domain. If you have a magnet like this, it can be separated into the domains. This is what we can call a domain, right? Now, inside the domain, the arrows will face the same direction like this, right? The same direction like this, right? In the same direction like this, right? They may have different directions, but within its domain, they're all gonna have the same direction, right? Let's just do it like that. They will have the same direction, right? Now with ferromagnets, they have the same direction, right? Actually, I could say with all of them, but I'm still focusing on ferromagnets. Now, these are lined up. With the permanent magnets, many domains are lined up, resulting in the net. What do we mean by that? In a permanent magnet, because this is a permanent magnet, if we have the different domains like that, we have the different domains like that, they all have the same direction, they are lined up, they follow the same line. If they're going to the right, they're all going to the right. If they're going to the left, they're all going to the left, depending on the direction of these domains, right? Now, the ferromagnets, these magnets that they use when they try to make cars nowadays, right? These magnets they use them to make sure that these cars brake faster. That is why we have the ABS braking system nowadays, because they're using the ferromagnets, right? When we say they're using a ferromagnet, what do we mean? We mean that the domains go in different directions. Many of us are familiar with Mercedes-Benz, for example, not promoting any brand, or even BMW. They all use the ferromagnets, right? These magnets, why do they use it in cars? They use it in cars because they are quick to attract, right? Because they do not, their domains are not in a fixed they are not in a fixed direction. They can attract very quickly, right? Now, I just wanted us to be familiar with the ferromagnets, right, in a real life situation. Now the permanent magnets, in the permanent magnet has got what we call the poles, right? This is a permanent magnet. Sorry. This is a permanent magnet, right? Let's say, let me do a better sketch. This is a permanent magnet, right? Being a permanent magnet, we're saying it has the poles, which means it has the north pole and it has the south pole, right? Now, remember what I said. They are all facing in the same direction. But let's now, before we go to the direction part, let's focus on this. Okay, the magnet will have the south pole and the north pole. Now, if we are to rip this into two, or to tear it into two, a permanent magnet will always have the south and the north pole. Meaning, if we have cut that magnet into two, this will be the north pole. We still have the second one is going to be the south, and this is going to be our north pole, right? We are still going to have the north pole and the south pole, right? Even if we are to cut this one into half again, we're still going to have the south, the north. We're still going to have the south, the north. In simple terms, we mean that the permanent magnets, we can say the permanent magnets, they are dipole, right? Now, in reality, is that there's no magnet that is monopole. All of them are dipole. They have the south pole and the north pole, right? Now, these are the poles. When we're speaking of the poles, we mean the sides. We have the south side and the north side of the permanent magnet, right? Now, if that is the case, we can get to the magnetic attraction and repulsion. There is this theory that we need to be familiar with, right? If you have above a magnet, and this is the north pole, let me write a beta N so that we can see that it's N, right? Yes, this is the north pole, this is the south pole, right? Then we have another magnet, this is the north pole and this is the south pole. Those magnets will never attract each other. We continue to say what? Sorry. I made a mistake. Let's say it's the south pole, right? And this is the north pole. I'm saying these poles will never attract each other, right? We continue to conclude and say what? Unlike poles do what? Repel, right? Because the poles are not the same, they repel, right? If the poles were the same, they were going to attract, right? Now, unlike poles repel. Now, what happens if we have the north pole, the south pole, right? The north pole and the south pole. What happens is that the like poles, the like poles do what? Attract each other, right? The like poles attract each other, right? That is basically the theory around the poles of permanent magnets. Unlike poles repel, like poles attract, right? Right. We can still use this domains to reason why these poles cannot attract each other. Remember, if these poles are going this way, it means that these poles are also going this way, right? Now, if they're going from north to south, or let's say from south to north, they are going like this, right? Now the domains will never interact, which will not allow this to be to interact with each other because of these arrows. For them to experience an attraction force between them, right, these arrows have to be facing directly each other, because these ones, if we say the domain is from south to north, right, no, yes, from south to north, they are going in the same direction. Therefore, they are going to do what? They are going to do what? they're going to attract each other, right? Mind you, let me make a simple correction. Not that the arrows do not interact, but that these arrows are going in the same direction. We can use a simple notation of vectors. Let's say this is what? This is 2 and this is 2 as well. This is 2 in the negative direction, 2 in the positive direction. If you say 2 minus 2, you'll get this as 0. Similarly here, if you have 3 and here you have 3, because they're going in the same direction, we say 3 plus 3 equals to 6, or we can say minus 3 equals to 6, right? Because they are going in the same direction. The domains, we can take them to be our vector part of the magnets. That's how I want us we understand these diagrams. Now, the permanent magnets, they have what we call the magnetic field lines, or the magnetic fields. Let's start with magnetic field. We said is a region in space in which the objects experience the attraction, or the non-contact force called the magnetic force. The non-contact force can be repulsion or attraction, right? Now, if that's the case, this magnetic field, they can be represented in terms of the magnetic field lines, right? Now, these are lines that are used to demonstrate the movement of forces, or the movement of, let's use the word forces of this specific magnet, bar of a magnet, right? Let's say we have this magnet and they say to you, show us the magnetic field. This is what you can do from north to south, right? Similarly, we are starting off on a simple note, right? From north to south, right? Now, if you still have to go further in this, or with this. All right, I will try to draw better arrows. You'll forgive me, guys. Yeah, I tried. Let me remove these ones. Right there. Right now, remember I said from North Pole to South, which means these ones, they are outgoing. These ones are outgoing. These ones are outgoing. They are outgoing, and these ones are incoming. These ones are incoming as well. Incoming as well. Right. These ones are always willing to accept. These ones are always willing not to say to accept. I want to use the electrostatic format, right? If we use the electrostatic format, we say this is the negative, this is the positive. This is willing to donate, this is willing to accept, right? Now, this means that this one is the one that initiates motion, and this one is the one that always accepts, because they're going in the same direction. 1 plus 1 is 2, right? Right. These are what we call the magnetic field. If they request you a question and say, draw the magnetic field lines, this is what you can do. This is how you can draw it. Right. You start by doing it like this, and like that, and like that, and then you start by doing beautiful arrows, right? Beautiful arrows. Yeah. You'll excuse me, guys. I'm not used to this. So yeah, then this is outgoing, this is outgoing, this is going this side, this is going this side, meaning this is the North Pole and this is the South Pole. This is incoming, this is incoming, this is incoming, this is incoming, this is going that side, going that side, right? This is basically what they want you to do. This is how they want you to represent them. Remember that from the positive side, they're always going out from the, from the North Pole, they're always going out. From the South Pole, they're always coming in, right? This is what you need to know. Right. This is the reason why magnets do not attract, or magnets attract. Let's say you have the North Pole. This is the South and this is the North, right? And this is the South, this is the North, right? We said this is going this side, right? And this is going outside like that, right? This is going outside like that. This is also going outside, right? Which means there's going to be repulsion, right? Either way, they will not fuse because the directions are computing each other, right? They are coming against each other, right? Unlike when it's the North, the South. Sorry, let's just use the same bar for magnet. If we flip the other one, and this is the South and this is the North, and this is the South and this is the North, right? Let me draw a better magnet. Yeah, let's say it's like that. Alright, let's say it's like that. This is the South Pole, this is the North Pole, right? This is going out, this is going out, and this is going this side. There is what we call motion, active motion between them, because they are willing to attract each other, right? These magnets will most likely attract, even if you had this side to be south and this side to be north, and this side to be north, this side to be south, they'll still attract because the arrows, they intertwine, right? Right. Ferromagnetism is a phenomenon shown by materials like iron and cobalt. These materials from the can form permanent magnets. They always magnetize as they attract to a magnet, right? No matter which magnetic pole is brought toward the unmagnetized iron, nickel or cobalt, right? Iron, nickel, and cobalt, CO, right? They always magnetize, right? Yeah, they always magnetize. The reason why they're called ferromagnet, the importance of ferromagnetism in cars or in anything is because they are always magnetized. It does not matter of these poles. Now, we can say ferromagnets don't have poles, but we cannot say that because every magnet has poles. It has not yet been proven that there is any magnet which has one pole or has no pole. So, what is the idea behind this? The idea is that ferromagnetism, they can attract each other regardless of poles, right? That is what we are told, right? Now, permanent materials and materials like aluminum, platinum, right, which become magnetized to an external magnetic field, right, in a similar way to ferromagnetic materials. They have the same properties, they're just a bit different. Now we have this is paramagnetic material. Then the diamagnetism is shown by materials like copper, right? bismuth, which become magnetized in a magnetic field with a polarity opposite to the external magnetic field. Unlike iron, they are slightly repelled by a magnet. Right. Now we have the compass. That we know that the Earth has got a specific magnetic field. The Earth has got a specific magnetic field. Right. The Earth has got a specific magnetic field. Now, the compass uses the Earth's magnetic field to find directions. Right. This is an instrument that was used a long time ago by travelers. Yes, anyone who was traveling, if they wanted a direction, they used the compass. Now, what you need to know is that the compass is at a specific angle to the north pole of the Earth's magnetic field. What do we mean by that? If this is the north pole, right, and this is the south pole, the compass is going to face more or less this direction, which means it's going to be in between 90 degrees and 0 degrees, right? Somewhat like this. Not so far, but in between. Yeah, that's right. It's going to be in between. This is the north pole, and this is the north side of the compass, right? Now, that is what we need to know, is that the compass, the magnetic field, will tell us the direction of the compass, but we need to know that the north pole of the Earth's magnetic field is not the same as the north pole of the compass. Now, we have magnetic poles and we have the geographic poles, right? Now, we have the magnetic poles. The magnetic poles are your north pole and your south poles, and we have the geographic poles, right? These ones we are not necessarily gonna get deeper into, but we need to know that the Earth has two poles. Has two north poles and two south poles, the geographic poles and the magnetic poles, right? That's what we need to know for now. Yes. Now we are on to the last part, the aurora. The aurora. Now, what is an aurora? This is a phenomenon whereby I want to explain it in simple terms. Let me try to explain it in a better way, so you can understand why we are speaking of an aurora, right? The Earth's magnetic, alright, when the charged particles from the solar wind reach the Earth's magnetosphere, they spiral along the magnetic field towards the north and the south poles, right? Now, when charged particles, right, from the solar wind, this is the outside, the solar wind, they do what? Reach the Earth's magnetosphere. Magnetosphere is a region whereby the Earth is a region where the Earth's magnet is, right? Now, they will spiral along, they will form the same patterns that you see on a bar of a magnet, but on the Earth, reflected on this Earth, right? The solar wind, the particles from the solar wind, they do what? They reach the Earth magnetosphere, they start showing patterns like this, right? In the atmosphere, you get to see it. because whatever happens is going to be reflected in the sky. Now that is what we call the aurora. If you can see it in the sky like that, those are when you can see the magnetic fields of the earth in the sky that are formed by the interaction of the particles of the solar wind and the earth's magnetosphere. Then you see something like this. Now, in aurora, we have the different kinds of the different names of it. There is the aurora borealis, right? Then we have the aurora australis, right? Yeah. Then that is basically the idea behind the aurora. We need to understand this concept of particles of the solar wind approaching the magnetosphere and then forming patterns like this, right? Yeah, that is basically what we need to be familiar with. Yeah, I'll leave you to research more on that. Then for any further question you may ask.